this is the 6th week, and today we will going to discuss questions on distribution of functions of several random variables. So before that, I will go through few fundamental theorems which will help us to solve the questions. So let's suppose we have a random variable from x1 x2 till xn. So these are known random variables. Now from this we need to find new random variables. These are unknown random variables. Unknown means their distribution is unknown. Okay, so we need to find distribution of these y1 y2 y3 to yk which are related to these random variable whose distribution we already know. So this y1 is some function of x1 x2 till xn. Similarly, y2 is some other function of all these random variables. So now given these things, we need to find distribution of new random variables y1, y2 and so on. So this is possible only when if these all gi's, like these the function which are, this is the functions relating y and x, if these functions are Borel measurable function, then we can say that all y's are random variable. If this property does not hold, then y is not a random variable. So this is an important property, that all the function gi's should be Borel measurable function. Okay. Now we will see how to calculate this the distribution for this unknown this y1s. So let's have probability that y1 is equal to small y1, y2 is equals to small y2, and yk equals to small yk. This is nothing but probability that g x1 till xn is equal to y1, probability that g x1 till xn is equal to y2, and so on. So this is nothing but summation over all the random variables x, known random variable x, given that probability that x1 is equals to small x1, x2 is equals to small x2, and so on, xn equal to small xn. This is the summation over all such x1s. Okay, so this is same as that this g x1 x2 xn is equal to y1. So for some particular quantities of x1 x2 x3 xn, this g of function is equal to y1. So we are putting all those values of x. Okay, now we will introduce a theorem. So let x comma y be a two-dimensional two-dimensional continuous type random variable with joint PDF fxy, then we can define some z which is the function of x comma y and another w which is another function of x comma y. So these z and w are random variables. Okay, so we are given that x and y are two-dimensional continuous random variables. Okay, and they have some joint probability distribution. This now we need, from this information we need to derive the distribution for z and w, where z is equal to some function of x and y and w is equal to some other function of x comma y. So now to solve this question, okay, so first assumption is, assume z is equal to x comma y and w is equal to h to x comma y. So now from this we will write x and y in terms of z and w. Okay, after doing that, now say x is equal to g1 z comma w and y is equal to g2 z comma w. Now this partial derivation of these, we will find the partial derivation of this rho x by rho z, rho x by rho w, rho y over rho z and rho y over rho w. Okay, so uh, we assume that all these exists and are continuous. Okay, all of these quantities exist and are continuous. This is the second assumption we made. So then the joint PDF for z comma w is nothing but probability x comma y. Now instead of x comma y we will write function of g1 z comma w and g2 z comma w multiplied by Jacobian of z comma w. This is a positive quantity of Jacobian, where this Jacobian is nothing but this thing, partial derivative, determinant of partial derivative of all of the random variable x and y with respect to z and w. Okay, and this cannot be 0. Okay, so this is the very important result, because from here we will from this formula we can solve any problems related to distribution functions of random variable. Okay, so some important results derived from this expression are this expression theorem. These are the first that uh, so for x and y are continuous random variable, then for z equal to x plus y the fz is equal to joint probability distribution where fxy exists, and we know this quantity. So then we substitute y from z minus x and then differentiate it over dx. Okay. Similarly, y equals to x minus y fz. These are two important results. And now we will try to solve few questions based on distribution functions of random variable. So first question. So this is the first question. We are given that x is a random variable with PDF that when x varies from 0 to 1 it is 2x and it is 0 otherwise. Then we need to find the PDF of y, which is 8x cube. So now we need to find the probability distribution function for y. So we are given that probability density function of x is 2x when x varies from 0 to 1 and it is 0 otherwise. And we need to find the PDF of y where y is 8x cube. Now first we will check the limits of y. So for x equal to 0, y is equal to 0. For x equal to 1, y is equal to 8. So limit of y is 0 to 8. Okay. Now this y is equal to 8x cube. So I will show uh, two procedures to solve this problem and you can find which suits best for you. So first method. Probability that y is less than small y. It is we replace y from 8x cube y. So probability that x is less than equal to y by 8 to the power 1 by 3. Okay. So this is nothing but probability fx dx varying from 0 to y to the power y divided by 8 to the power 1 by 3. Fx is 2x dx from, so this will be minus infinity to this y by 8 to the power 1 by 3, but as we know that x varies from 0 to 1, so this lower limit will change from 0 to y by 8 to the power 1 by 3. So this is nothing but, this comes out to be, when we solve this, y to the power 2 by 3 divided by 4. Okay. So now this is CDF of y. So for PDF, we will differentiate this CDF with respect to y, and we will get that this is equal to 1 divided by 6 to the power 1 by 3, or y to the power minus 1 by 3 divided by 6. So when y varies from 0 to 8 and it is 0 otherwise. Second method could be, we will, it is given that y is equal to ax cube, we will write x in the form of y, and then we will find this dx by dy, which is 1 by 3 y to the power 1 by 3 minus 1 divided by 8. This is 1 upon 16 y to the power 2 by 3, right? Now fy is nothing but fx, yeah, oh it's 1 by 3, sorry. So this will be 1 by 24. Thank you. So, check it again. हाँ. Okay, it's plus 2 by 3. And this will be 8 to the power 1 by 3, which is nothing but 2. So this will be 6. So I will write it again. Y to the power minus 2 by 3. 3 into 2 the power 3 divided by 1 the power 1 by 3. So this is y minus 2 by 3 divided by 6. Okay. So now this y is nothing but probability density function of x divided by multiplied by dx dy. Okay. This is from the property I discussed earlier. Now fx is 2x. Just okay. So it won't be solved using this thing. It will become difficult. Or sorry. Instead of small x, we will write y to the power 8 power 1 by 3 into dx by dy. We replaced this x by this thing. So now this is nothing but 2 into y to the power 1 by 3 divided by 8. This quantity is y to the power minus 2 by 3 divided by 6. So now this is 4. Okay, this will be okay. So this 8 to the power 1 by 3. So this 2 will cancel out, and this expression will converge to y to the power minus 1 by 3 divided by 6. Right? So, and in the previous method we saw that this was the PDF for the function. So here we use the property that if y is given in terms of x, then we can write x in terms of y. Then this PDF of y is equal to PDF of x, and instead of small x we will write it in expression of this function gy and multiply it by dx by dy, or this, or I can say better expression will be this probability distribution. Sorry, no. Gy. I'm sorry. So we reduce the previous two-dimensional results into one-dimensional result. This is dgy by dy. So this is nothing but dx by dy. So from this we can calculate this PDF of y. And there was the other method where we solve it using the basic method, where we write y in the terms of x and then x in terms of y, and then solve this expression from here to from range of x. So in a way these both things are same, but so this, by using the second method we can solve questions in lesser time. So this is more efficient, a more efficient method, because we need to directly use this formula. Okay, so moving on to the next question. So this is the question where x is a continuous random variable with PDF given in the expression, and now we need to find the distribution of y, where y is x square. So just try to do this question. I just give you 2 minutes. So it uses the methodology will be the same as the previous question, but now this function will be something else for minus infinity to 0, and from 0 to infinity it is something else. So we need to decide the range for y. Okay, so just try to solve it once and then I will discuss this. Okay, so this fx is given as mod x ranges from minus infinity to infinity and 0 otherwise. This can be written as 1 to the power 1 by 2 e to the power, when we when x belongs to minus infinity to 0, this will open as a negative with the negative sign, and this will be e to the power x, and when x belongs to 0 to infinity, the mod will open with the positive value, and this expression will become half e to the power minus x, and it is 0 otherwise. Now we need to find the probability distribution for y, small y, where probability y is x square. I can write it as so now I can integrate my fx function from minus root y to root y. So I like to solve the problem with this method because it is more fundamental. So you can try the second method which I told earlier. So I will just show the results of this question. So now this is from minus infinity to from minus root y to root y. Now we will separate this limit negative, because we know up to 0 it is different, and from 0 it is slightly different. The function is slightly different. So first we will find this minus root y 0. So this is e to the power x by 2 dx minus root y 0. So this comes out to be 1 minus e to the power minus root y divided by 2. Similarly, we will find it for the range 0 to root y, where it open as e to the power minus x by 2 dx 0 to root y. This will become 1 minus e to the power minus root y by 2. Okay, so this probability y less than equal to y is summation of from minus root y to 0 plus some integration from 0 to root y. So we found these two are equal. 1 minus e to the 1 minus root y by 2. So this is nothing but 1 minus e to the power root y. Okay, this is the CDF. By differentiating this, we can find the PDF of function. Okay, so this is the CDF. So I hope this is clear. So now moving to the next question. So here it is given that y is a continuous random variable and with PDF given in the expression. Now we need to find the conditional probability for y less than equal to 2 by 3 given that y is greater than 1 by 3. So this fy is given as 5y cube when y ranges from 0 to 1, and it is 0 otherwise. We need to find the probability that y is less than equal to 2 by 3 given that y is greater than 1 by 3. So this is nothing but, yeah, okay, yeah, no, it is visible. So this can be written as probability y less than equal to 2 by 3, comma, y is greater than 1 by 3 divided by probability that y is greater than 1 by 3. So this is saying that this is 2 by 3, this is 1 by 3, here it is 1, this is 0. So y is from 0 to 1. This expression is saying that y should be less than equal to 2 by 3, and this expression is saying that y should be greater than 1 by 3. So this is the common region. So here this y will range from 1 by 3 to 2 by 3. This is nothing but probability that y is greater than 1 by 3 and less than 2 by 3, and divided by probability that y is greater than 1 by 3. So we know the PDF of random variable y. So this probability becomes fy dy ranges from 1 by 3 to 2 by 3 divided by probability integrating this probability mass function from range 1 by 3 up to 1, because it is saying that y should be greater than 1 by 3 and y limits of y is from 0 to 1. Therefore this the limit for this integration is from 1 by 3 to 1. So this is 5y cube dy 1 by 3 to 2 by 3 divided by 5y cube 1 by 3 to 1. So these 5 will be cancelled out. And this becomes y to the power 4 from 1 by 3 to 2 by 3, y to the power 4 1 by 3 to 1. So this, there will be 4 and 4 here, so these get cancelled out. So this will this come out to be 15 by 80. Okay. So I hope this is clear. So now we move to the next question. So here we are given that x is a continuous random variable with some probability which the probability density function is given in the expression, and we are given the expected expected value of x, random variable x, expectation of random variable, and then we need to find the value of alpha and beta. So try to solve this question. So this is an easy one. So just try to solve it. I will give you 2 minutes. So which two results you are going to use for this question? Because there are two variables alpha and beta, so we require two equations. So one is this expectation is equal to 3 by 5. So one is x fx integrating from 0 to 1 is equal to 3 by 5. And another will be okay. So we are given this fx function x ranges from 0 to 1 and it is 0 otherwise. So if expectation of x is 3 by 5, then we need to find the values of alpha and beta. So one thing that is given is no, it is alpha plus beta x. Oh sorry, it's x square. Sorry. So this is given as 3 by 5. X fx is given as 3 by 5. So we will try to solve this. So alpha x square by 2 plus beta x to the power 4 by 4 from 0 to 1 is equal to 3 by 5. So this will give us the equation alpha by 2 plus beta by 4 is equal to 3 by 5. Okay, this is one equation. Then we also know that fx dx from 0 to 1 is equal to 1. Probability density function for the whole limit is 1. So this will become alpha plus beta x square dx from 0 to 1 is equal to 1. So alpha x plus beta x cubed by 3 from 0 to 1 is equal to 1. So this is alpha plus beta by 3 is equal to 1. So this is the second equation. So we can write from equation 2 that beta is equal to 1 minus alpha into 3 and put it into the first equation where alpha by 2 plus 3 1 minus alpha by 4 equals to 3 by 5. From here we will get that alpha is equal to 3 by 5 and beta is equal to 6 by 5. So this result is very crucial, that fx dx over the whole range is equal to 1. And the formula of expectation is also important, that it is x fx from 0 to 1. So these two results are used to solve this problem. So now we move to the next question. So here this x and y are discrete random variable with joint probability mass function given in the expression, and then we need to find the conditional probability that if I for x equal to 1 given that y is equal to 0, and second is probability that x is equal to 2 given that y is equal to 0. So we can make a table like this. X is varying from x is 0 and 1 and y is varying from 0 1 2. So when both are 0, this is x is 1 and 2. So for 1 comma 0 probability is 1 by 4. For 2 comma 0 probability is 1 by 4. For x equal to 1 and y equal to 1, the probability is 1 by 4. For x equal to 1 and y equal to 2, the probability is 1 by 4. And for x equal to 2 and y equal to 1, probability is 0. And for x equal to 2 and y equal to 2, the probability is 0. We need to find that probability that x is equal to 1 given that y is equal to 0. So this is nothing but probability that x is equal to 1 comma y equal to 0 divided by probability that y is equal to 0. So this the probability that x is equal to 1 and y is equal to 0 is x is equal to 1 and y is equal to 0. The probability is 1 by 4. 1 by 4 divided by probability that y is equal to 0. So y is equal to 0 is 1 by 4 plus 1 by 4, which is 1 by 2. So this divided by 1 by 2. So this becomes 1 by 2. Okay. So this you understand that y probability of y equal to 0 is 1 by 4 plus 1 by 4. Okay. So that's why this probability y equal to 0 is 1 by 2. And probability that x equal to 1 and y equal to 0 is given in the table itself, which is 1 by 4. Similarly, this probability x equal to 2 given that y equal to 0 is nothing but probability x equal to 2 given and y equal to 2 divided by probability y equal to 0. So probability that x is equal to 2 and y equal to 0 is 1 by 4. Again it's 1 by 4. And we know that probability of y equal to 0 is 1 by 2. So this again comes out to be 1 by 2. Okay. So now we move to the next question. So this is quite a good question. So let x be a continuous random variable with probability density function given in the expression, and y is equal to 2 divided by x plus 4. Then we need to find the variance of y. Okay. Just note down the question. So this fx is given as x square 2x plus 3 by 2, where x varies from 0 to 1 and it is 0 otherwise. Now this expectation, we will find this first we will find the expectation of x. Okay. So this is nothing but fx dx 0 to 1, which is x cube. Okay, sorry. So this fx is given as this, and the expectation is equal to x fx. So this x cube 2x plus 3 by 2 dx 0 to 1. So this is 2x to the power 5 by 5 plus 3x to the power 4 by 8 from 0 to 1, and this comes out to be 31 by 40. Okay. Now this variance of x is expectation of x square minus expectation of x to the whole square. So we need to find this expectation of x square, which is nothing but x square fx dx 0 to 1. So this is x to the power 4 2x plus 3 by 2 dx. So this is 0 to 1. This comes out to be 2 by 6 plus 3 by 10 20 38 by 60. So variance of x is expectation of x square minus expectation of x whole square. So 38 divided by 60 minus 31 by 4, 31 by 40. This is nothing but 19 by 30. Okay. So this expectation of x is 31 by 40 and variance of x is 19 by 30. So this is whole square. Now y is given as 2x plus 4. So the variance of y is equal to variance of 2x plus 4. So this 2 is a constant, and we know that variance of alpha x is equal to alpha square variance of x. So using this property, we can write that variance of y is 4 variance of 1 by x plus 4. And we also know that variance of a plus x, where a is a constant, this will remain as variance of x. So using this property, variance of y is equal to 4 into variance of 1 by x. So this 1 by x can be treated as a z function. Okay. Okay, so this is so now we consider this 1 by x as a function z. Okay, so we can write x in terms of z, which is this x is equal to 1 by z. Okay, so now we need to find this variance of 1 by x. This is nothing but expectation of 1 by x square minus expectation of 1 by x to the power whole square. First we will find the expectation of 1 by x. So this is nothing but e z. Z is the function of x. Okay, so z is equal to 1 by x, or we can write it as a function of x, right? So this will be from the so using the property that expectation of gx is nothing but gx into fx dx minus infinity to infinity. This is the Lotus property. So this g function is 1 by x. G of x is 1 by x. So expectation of 1 by x becomes 1 by x into fx dx minus infinity to infinity. We know this fx. This is x square 2x plus 3 by 2, where x varies from 0 to 1. So this is x 2x plus 3 by 2 dx 0 to 1. So this comes out to be 13 by 12. Okay, 13, sorry, 17. Now we will find this expectation of 1 by x square. This is nothing but fx dx by x square dx minus infinity to infinity. And this is nothing but x square 2x plus 3 by 2 divided by x square dx 0 to 1. This becomes simplifies to 2x plus 3 by 2 dx 0 to 1, and this comes out to be 5 by 2. So now we know the variance of 1 by x is expectation of 1 by x square minus expectation of 1 by x to the power 2. This comes out to be 71 by 144. So variance of y is 4 into variance of 1 by x. So this is 4 into 71 by 144, which is 71 by 36. Okay. So from this x, we to find the this variance of 1 by x, we consider a function gx which is equal to 1 by x, and then use the Lotus property, this Lotus property, that expectation of a function of random variable is nothing but that function into PDF of the random variable. So I hope this is clear. So now we move to the next question. So let x is a uniform probability distribution from -1 to 4, from -1 to 4, and let y is equal to 2x plus 5. Then we need to find the PDF of y. So this is similar as the questions we have done before. So can you try this on your own? Just try it, because this is the we discussed few questions based on this idea. We are given that x is a uniform distribution from -1 to 4, and y is equal to 2x plus 5. Now we can write x in terms of y using this equation, and we call it as a g function. So this probability of y is nothing but probability density function of x into the mod of differentiation of gy by dy. Okay, so just try to put the values now. You need to figure out the range of y as well. The range of x is from -1 to 4. So using this formula, you first need to find the limits of y. Then change this equation by uh, by moving all the terms in the LHS side and making it a expression x equal to some function of y. Then find the differentiate this function with respect to y, take its mod and multiply it with the probability density function of x, and you will get the probability density function of y. So y is equal to 2x plus 5. So x is equal to y minus 5 by 2. So dx by dy is equal to 1 by 2. Now this y is 2x plus 5. So for x is equal to minus 1, this y is equal to 3. And for x is equal to 4, y is equal to 13. Okay, so this is the range for y. Now this fyy is nothing but fx into this dx by dy. So this fx is this is given as a uniform distribution, so which means that this will be 1 divided by b minus a when x varies from a to b and it is 0 otherwise. A is minus 1, b is equal to 4. So this fx is 1 by 4 minus minus 1 when x varies from minus 1 to 4 and 0 otherwise. So this is 1 by 5 when x is from minus 1 to 4 and it is 0 otherwise. Now fy is fxx into dx by dy. So this is 1 by 5 into 1 by 2, which is 1 by 10. So this fy is 1 by 10 when y varies from 3 to 13. We saw that for the range of x from minus 1 to 4, the y ranges from 3 to 13 and it will be 0 otherwise. This is also uniform distribution from 3 to 13. So we can see that 13, this fyy is equal to 1 upon b minus a, where x ranges from b to a. Here a is 3 and b is 13. 13 minus 3 is 10. So this is y is also a uniform distribution from 3 to 13. So I hope this is clear. Yeah, for all the problems you need to find out the limits, because this y is the function of some random variable, and if that random variable has a range, then we need to find the range for y as well. This is the similar question, but now this y is given as e to the power minus 2x. Now we need to find the PDF of y. So it will be also the same. X is a uniform distribution and y is e to the power minus 2x. So this y is equal to e to the power minus 2x. So we can write x in terms of y from this, which is minus 1 by 2 ln y, and dx by dy becomes nothing but minus 1 by 2. Okay, minus 1 by 2, this is the constant, and ln y, differentiation of ln y will be 1 by y. This is minus 1 upon 2y. Now x is a uniform distribution, right, from 0 to 3. So we will see for x equal to 0, y is equal to 1, and for x equal to 3, y is equal to e to the power minus 6. So range of y is range of y is e to the power minus 6 to 1. Okay. So now again this y will be nothing but fx into dx by dy. So this is nothing but 1 by 3 when x varies from 0 to 3 into dx dy, which is dx by dy is minus 1 upon 2y. This there is a mod, so this negative value will cancel out. So which will become 1 by this minus, so this comes out to be 1 upon 2y, which is 1 by 6y when x ranges from 0 to 3 or y ranges from e to the power minus 6 to 1 and 0 otherwise. This is the PDF of y 1 upon 6y, where y ranges from e to the power minus 6 to 1, and it will be 0 otherwise. Okay. So whenever you are given a random variable x with some probability density function and you need to find the probability density function of other random variable which is given in form of some function of x, then we will first, so if we are given some function of x, first step is to find the range, find range of y from given from gx and given range of x. Then write x in terms of y, some function y. Then find dhy by y. Now this probability density function for random variable y is nothing but probability density function of x into dhy by dy. So these are the 3 easy steps to solve such kind of problems. Now we move to the next question. So here x and y are both uniformly distributed in ranges of minus 1 to 1 and minus 2 to 1 respectively. Let z is equal to x plus y. Then we need to know what is the probability that z is less than minus 1 by 2. Okay. So first we need to find this probability density function for z. So x is a uniform distribution from minus 1 to 1. Y is a uniform distribution from minus 1 to 2. Minus 2 to 1. Z is equal to x plus y, and we need to find the probability z is less than equal to minus 1 by 2. So in the starting of the chapter So this first we need to find this probab joint probability distribution of x comma y. So in the question, so x and y, so here x and y are independent. Okay, it is not given in the question, but it is independent. I forgot to write that they are independent uniform distribution. Or you can find it as well. So uh, so to check whether these are independent, we will see that f of x comma y is equal f x. So no, we cannot, because this probability mass function is not joint probability mass function is not given. So these are independent. It is, I forgot to mention in the question. These are independent. So this joint probability distribution is easy to find, which is nothing but fx fy fx into fy. So this is the uniform distribution from 1 to -1. So this is 1 upon 2, and this is 1 upon 3. 1 minus -2, so this will be 1 by 3. So this is 1 by 6. This joint probability distribution is 1 by 6. Okay. Now this z is equal to x plus y, and we in the starting of the lecture we discussed a property that for such function this is nothing but probability density function x y x comma z minus x dx, where this ranges from minus infinity to infinity. So this is nothing when we put it. So this is 1 by 6 fx dx from x to z minus x. So this probability density function, this is also a uniform distribution. So this probability density function for fxy x comma z minus x, this is nothing but this is 1 by 6, and this is integrated over whole dx, where x ranges to -1 to 1. So this is nothing but x by 6 minus 1 to 1, which is 1 by 3. Okay. Now we need to find the probability. Sorry. We need to find the range of x, y, z. So for I just wait. First we find range of y. this x is minus 1, 0, 1, y is minus 2, minus 1, 0, 1. Okay, so these are all the combinations possible. There are 3 cross 4, there are 12 combinations. So this smallest value for x plus y is minus 3, minus 1 plus minus 2, and minimum and maximum is 2. So x has these 3 values and y has these 4 values. Okay, so maximum of x plus y is 2, minimum of x plus y is minus 3. So z ranges from minus 3 to 2. Okay. Okay, sorry, it is minus 3. So it is minus 3 to 2. Minus 3 to minus 2. We need to find the probability that z is... No, here it is for dx, right? So that's why we will use the limits for x. And this expression is nothing but 1 by 6. So this comes out to be dx by 6, which will become x by 6 from minus 1 to 1. And this is nothing but 1 by 3. Now this is the probability density function for z. So the probability that z is less than equal to minus 2 is nothing but integrating this 1 by 3, and range of z is from minus 3, and it is given that it should be less than minus 2 is minus 2. So z by 3 from minus 3 to minus 2, minus 2 plus 3, this comes out to be 1 by 3. Okay, so the probability that z is less than equal to minus 2 is nothing but 1 by 3. Okay, so if this joint probability distribution function was in this form, in the form of some x y, then instead of y we will write z minus x, and then solve it in the expression for z. Okay, but here it is given only 1 by 6. It's a constant quantity, that's why it is only it is coming out as a constant value. So these are the all questions I am going to discuss today. So if you have any questions, you can ask, or we can end the meeting. Okay. So if you have any doubt, you can ask in the next session. Okay.